Hello, rocket builders. One of the things that makes model rocketry different is we use parachutes to recover the rockets, allows us to change the engines and fly them again. The Saturn 1B is no different. There is a standard technique for the high flyers called dual deployment, and in many ways the Saturn 1B is a typical dual deployment high power rocket. But as with everything, there are enough challenges in the Saturn 1B to make this an interesting aspect of the build. And that's what we're going to look at today. So stay tuned. Remember folks, I've been certified to build and fly rockets up to level 3. If you don't have these qualifications, you might want to consider a simpler project and perhaps join one of your local or national organizations. Rocketry is a very safe hobby if you follow some very simple guidelines. Okay, so first of all, what is dual deployment? Well, this is a method of recovery that uses multiple parachutes. When the rocket reaches its highest point, a small parachute will come out and it will descend at a relatively fast rate, but still enough to keep it in control. And the fast descent rate allows it to land fairly close to the launch pad, so you don't have to walk as far to recover your rocket. And then when you are a certain altitude above the ground, typically around 1,000 feet, you would deploy a second larger parachute that will then slow it to its final descent speed, allowing it to land safely without hurting anyone on the ground and without breaking any parts off the rocket. That's what this rocket does. Now, typically speaking, a rocket will break into two pieces. So if we look at my level 3 rocket, for example, the first separation break is around the middle. This allows it to deploy what's known as the drogue chute, which is a smaller parachute that does the initial descent. When it's close to the ground, it would deploy a second charge, ejecting the main parachute from the front end of the rocket, and this is what allows it to land safely. So we do the same thing here. Now with the Saturn 1B, we've actually got a slightly different body design. It's actually like a rocket within a rocket. So we have a very large body tube, certainly much larger than this one. That's about 12 inches in diameter. Okay, and we use a smaller tube that's actually 5 inches at its biggest, 3 inches at its smallest inside. Okay, so this is known as a stuffer tube. So all of the structural weight of the rocket is actually on this center tube, and the outer section is just a facade. We also contain all the ejection charges within the center tube. A 5-inch tube is easier to pressurize to eject a parachute than a 12-inch one. Certainly takes a lot less black powder, and that saves weight, it saves black powder, and it saves on the danger of having a very large boom in the middle of your rocket. So very desirable. We use what's known as blue tube for the intersection, and the outer shell, like I said, just a facade, is the homemade fiberglass section that I made. Okay, so like the level 3 rocket I showed you earlier, the rocket actually splits into two pieces about midway, okay, and the smaller drogue chute is contained in the lower section, okay, so it'll come down in two halves fairly quickly. When it gets near the ground, the nose cone will be ejected and the larger main chute will come out from there. Okay, now it is complicated a bit because it is a tube within a tube, and that has some issues that we'll talk about later. Okay, but for the most part, it's pretty standard high power rocketry. When I did my level 2 certification, that's the first time I actually did that on a rocket, and it worked quite well. So when you're talking dual deployment, you can't use the ejection charge in the motor like you can with the low power rockets. So we have to have electronics to control this. And this is one of the devices that I used in the Saturn 1B. This is a device made by a company called Altus Metrum, and it is their telemetry recovery controller. Now it has a number of interesting features: a GPS and a ham radio link, and this pair provides some very important functionality for us. The ham radio link allows us to broadcast while we're flying, so we can get real-time information about speed, about location, about altitude, and so on. When paired with the GPS, yes, it can give us some of that information, but the GPS doesn't react fast enough while it's flying. The key feature of the GPS is it sends its location once it's landed, and we know where to go to look for it. I've lost a lot of smaller rockets, and believe me, this thing has saved me a lot of time and effort. But that's not the main functionality. So the main functionality, there are two types of sensors on here. One is a barometric sensor, and it measures air pressure. Now, air pressure decreases as you increase altitude. So by measuring the difference between where you started and the current air pressure, you have an idea about how high you are. Now, the other thing about it too is it can also sense when you're at the peak. So when the air pressure stops falling, you know you're at your peak. Now, there are some quirks about that. For example, you get a little dip in air pressure as you start to go supersonic. Not an issue with this rocket, but certainly with some others I've flown. There is also an accelerometer on board, which can measure the acceleration forces in the X, Y, and Z coordinates. It's generally used as a backup to the barometer, but it certainly helps with things like the dip in pressure during the transonic period. Okay, so both those sensors are collecting data. It saves it to memory so that we have a record of the flight afterwards, and that's how I'm able to produce some of the nice graphics showing our flight. Okay, now this is not the only one out there. There are other models as well. Okay, there is an onboard computer for this, and we program it both how we want the drogue and main chutes to fire. In this case, this is my primary computer. So it will fire the drogue at peak altitude, and then my main parachute at a preset height above the ground. Now, things fail. I don't think I've had a flight yet where I haven't had to do a last-minute substitution of flight computers. Certainly for both my level 2 and my level 3 certification, I had to do a substitution. Now, because of that, we fly with two computers. Okay, so if the main computer tells the drogue chute to open at the highest point, the backup computer will tell it to open at the highest point plus a half second. Similarly, when this fires at 1,000 feet, this would tell it to fire at 800 feet. That way, one of the two computers is going to ensure that we actually have the parachutes opening. The parachute's not opening is a very bad day. Okay, now my backup computer is a lot simpler and therefore less expensive. Okay, so this one just has the barometer and the accelerometer sensors. Okay, but between the two of them, I have redundant controls. That is a requirement for flights above a certain size. Certainly for your level 3 flights, you require redundant computers. Okay, now on the back side of these, I have spaces for the batteries. They take different types. This is a lithium polymer. This is a regular 9-volt battery. We also have holes in them so that they can go onto a threaded rod and be placed into the rocket. Now, another thing I've done with these is I've made them interchangeable. So I can use them in a number of different rockets and a number of different configurations. So for example, in a narrower body tube, I can have them lined up right next to each other. And of course, I have the slot for the antenna to be held in place when I have the two of them in a vertical alignment. In this particular rocket, we actually just have enough space for them in separate compartments, and I'll talk about that in a moment. And we also have to make accommodations for the antenna. Okay, so one of the things about the electronics that I've already mentioned is that it uses a barometric sensor to measure changes in pressure. Now, if I just put this on the inside of the rocket, obviously we have a problem because the air pressure isn't going to change. It's going to stay constant inside the rocket while it's the air pressure outside that changes. So, a little bit of rocket science here. We need to drill some holes in the side of the rocket to let air in so that we can actually detect the differences. Now, for other rockets, that's typically pretty easy. They have small diameters. You drill some holes in the electronics bay that holds the electronics, and the air comes in. We measure the differences. Okay, So there is a pressure calculator that I used online, and I'll have the link below. And it basically tells you how big a hole you need on the side of your rocket based on the number of holes and the volume that this sits in. Okay, so if it's in a small compartment, we can get away with a smaller hole because it lets lets enough air in for us to measure the difference. But if we're in a bigger compartment, we need a lot of air coming in. Okay, so for a typical rocket, that's not too bad. You're in a small electronics bay, which is, maybe 12 or 18 inches long. And you just drill some holes through the same place where you go to look for the switches. It works out fairly well. Certainly that's what I did with my level 3 rocket. Now this rocket presents some challenges for a few reasons. One is the main body tube is external to the internal body tube. Okay, so the electronics bay doesn't even sit on the outside of the rocket. So that's one of the problems. Another problem is that external body tube is a very large volume. It's 12 inches round and a few feet long. So in order to achieve enough air exchange to detect those pressure changes, we need some pretty big holes and a lot of them. I didn't want to do that. Now, if we look at the diagram of the rocket, you will see what are known as ullage motors. So the ullage motor sits on the side of the rocket and it looks kind of like this. Now, the purpose of the ullage motor is when the rocket's flying up in space, the tank isn't completely full. So if the motor is at this end and all the fuel is at this end, you're not going to get very far. So what the ullage motor does, okay, so if we place it on this side, it fires, provides some thrust, so all of the fuel is pushed to the side that has the motor. We can successfully fire, and off we go. Okay, so why is this important for us? Well, if we look at the profile of the ullage motor, one of the things that allows us to do is to hide a small hole that can go all the way through to the inside of the rocket. This is going to be our vent hole. Okay, so based on the diameter of that hole and the volume inside of our rocket, what we're going to do is we're going to put a couple of barriers to reduce the volume in which we have to provide air. Okay, so it has to be long enough to contain one of the flight computers, obviously, but other than that, we have a few options. So remember, we have a body tube within a body tube. We know how much air pressure we can detect based on the size of the holes. There are 3 of these around the outside of the rocket. So what we do is we take the area of the cross-section of the outer tube, subtract the area of the cross-section of the inner tube, and what we need to do is determine what length will provide that acceptable volume. And that's what we did. So in the picture, you can see the threaded rod that the computers are mounted on. Now what you can't see is we have the antenna. Now with a small compartment, that antenna is rather inconvenient. So what I did was I got a plexiglass tube, blocked one of the ends with epoxy, and drilled a hole in the compartment at the end of the rods so that the antenna can slide into that hole and we can still get communications. Now incidentally, that's why the upper part of the rocket is made with fiberglass and not carbon fiber, so that we can still get radio connectivity. Okay, now I haven't shown you the wiring for this, but there are switches that need to turn this on and activate it before we fly. Obviously, we don't want to turn that on until we get to the launch pad so that we don't have black powder exploding prematurely. So that switch needs to be accessible. Again, if we go back to the diagram of the Saturn 1B, we see that there's a small hatch shown here. Well, I put a hatch in the model at the same place, and the switch can be viewed from inside that hatch. So open the hatch, turn the on button. There are actually two of them for both of these flight computers, and also for the redundant timers for the clustering, but we'll talk about that in a future video. Now, the eBay itself, like I said, we don't have external access to that like we did in my level 3 rocket. So we actually just pass the wires into that inner eBay, and the only thing on the ends of the eBays are the casings that hold the black powder charges that will eject the parachutes. So that's the recovery for the Saturn 1B. In many ways, it is pretty much standard dual deployment. We had to get a little bit creative about where we put the ejection charges and how the wiring was done. A little creative with the vent holes so that we don't spoil the scale effects of the rocket and still get reliable recovery. But it's really a straightforward application of the standard well-known principles of dual deployment that we use in high-powered rocketry.